I hope you have watched my previous videos on van der Waals bonds and metallic bonds. Another type of chemical bond is an ionic bond. Ionic bonds involve a bond formed between atoms as a result of one atom donating one or more electrons to a second atom. A common ionically bonded substance is table salt. Ordinary table salt is sodium chloride, or NaCl. Sea salt is composed predominantly of sodium chloride, but will also contain various amounts of other salts, including potassium chloride and magnesium chloride. These other salts are also ionically bonded. If we look just at sodium chloride, we see that sodium Na is a first column element, meaning it has one valence electron in the 3s shell. If it can lose that one valence electron, it would have the same valence electron structure as the noble gas neon. Neon has an octet of valence electrons in its second energy level. Sodium will readily lose that 1/3 energy level valence electron to obtain the same valence electron structure as neon. For sodium, the valence structure of neon is a lower energy state than if it hung on to that one electron in its third energy level. For chlorine, Cl, we see that it is in the column 17 halogen group. Chlorine has 7 valence electrons. If a chlorine atom can gain just one more electron, it will have the same octet of valence electrons as the noble gas argon, Ar. The energy state of the argon electron cloud is lower than the energy state of the chlorine electron cloud. Chlorine will readily accept the one valence electron that the sodium needs to lose to achieve a lower energy state. Sodium chloride is the perfect ionic bond pairing. One atom wants to lose an electron, and the second atom wants to gain one electron. By pairing, sodium and chlorine each satisfied their own needs to get an octet of valence electrons and be in the lowest energy state. When sodium and chlorine bond, they give off heat energy that is exactly equal to the difference between their original energy and lower energy states that both have achieved. This heat released is the bond energy, also called the heat of reaction or the enthalpy of formation. Other ionically bonded compounds include potassium chloride and calcium chloride. Potassium chloride is a common dietary salt substitute for sodium chloride. Some advertisers sell potassium chloride as light salt because the potassium is substituted for the sodium in sodium chloride. If we look on the periodic table, potassium K is in the same column as sodium Na. Like sodium, potassium readily donates an electron to chlorine, so both can achieve an octet of valence electrons. Potassium chloride tastes salty like sodium chloride, but the salt taste is weaker with some bitterness. As we go down the first column of the periodic table, the elements grow more reactive as their electron clouds grow larger and less tightly bound to the protons in the nucleus. We could predict any first column element bound with chlorine would taste salty. Only lithium chloride has the same saltiness as sodium chloride. Calcium chloride is another ionic salt. Calcium chloride is most often found in road salt used for melting snow and ice. Calcium chloride is preferred over sodium chloride as an ice melt because it is less reactive in eroding concrete road surfaces. As a second column element, we should know that calcium Ca has 2 valence electrons. Calcium needs to donate these 2 electrons to achieve the same valence octet as argon. This is why calcium binds with 2 chlorine atoms to form CaCl2. Each chlorine atom receives one of the donated electrons from the calcium atom. So by accepting one electron, each chlorine achieves its own octet of valence electrons to have the same electron structure as the noble gas argon. In solid form, ionically bonded pairs are strongly bonded. Neither the electron donor nor the electron acceptor will go back to its higher energy state without cause. The solid ionic crystal lattice is bound together by the mutual attraction of the positive and negative ions of which it is composed. One fact about ionic salts is they readily dissolve in water. Approximately 350 grams of table salt will dissolve in a liter of cold water. Around 400 grams of salt will dissolve in a liter of near boiling water. Put more salt in than that and it will precipitate out and sink to the bottom of the container. In solutions of ionically bonded substances, the constituents will ionize. An aqueous solution of sodium chloride, NaCl, will contain Na+ ions and Cl- ions. These ions float freely in the water, suspended and only loosely bound by hydrogen bonds to the polarized water molecules surrounding them. The ions in the dissolved water change the properties of water, including making the water denser or lighter and making the water a better conductor of electricity. The ions in an aqueous solution are free to bind with other atoms or ions present in the solution, and will do so if the overall effect is to reduce the energy of the system. The desire of all nature is to be in the lowest energy state, or at least in equilibrium with its surroundings. The ability of ions in solution to interact with other substances will be important if we want to understand biology or batteries or any other wet chemistry. Covalent bonding is another type of chemical bonding. Like ionic bonds and metallic bonds, covalent bonds help atoms achieve a full octet or 8 valence electrons in their outermost electron shell. In ionic bonds, one atom donates electrons and the other atom receives electrons, and so both get an octet. In covalent bonding, the atoms cooperate to share valence electrons so that each atom in the covalent bond receives an octet of valence electrons by commingling their electron clouds, emphasis on co-words. There are 2 degrees of covalent bonding: polar covalent bonds and nonpolar covalent bonds. The difference between polar and nonpolar covalent bonds is the degree to which the electrons are shared. For example, the element oxygen rarely exists as single atoms except at very high temperatures. At normal temperatures, nearly all the oxygen in a room will exist as molecular oxygen, O2. O2 is a molecule of 2 oxygen atoms that are nonpolar covalently bonded. Both O atoms need 2 electrons to complete their octets. Both equally share the 2 valence electrons that will complete their octets. The figure contains a Lewis diagram showing the representation of 2 oxygen atoms with 6 valence electrons each, and the double bonding that indicating that they share 2 of each other's valence electrons. If one counts the total valence electrons around each O atom, including the shared electrons, one will count 8 valence electrons. As it contains a double bond, O2 is a strongly bonded molecule. As neither atomic O nucleus has a dominant pull on the valence electrons of the other, the oxygen molecule is a nonpolar covalently bonded molecule. Nitrogen, N2, is another gas that has a nonpolar covalent bond. In the case of nitrogen, N2, each N atom requires 3 valence electrons to gain a full octet. N2 has a triple nonpolar covalent bond. The figure contains a Lewis diagram representing the 2 nitrogen atoms with 5 valence electrons each, and a triple bond indicating that they share 3 of each other's valence electrons. One can count the 8 valence electrons around each N atom. The triple bond of N2 is extremely strong. The triple bond is so strong that nitrogen gas is inert in most cases. Nitrogen is often used as a buffer gas in industries such as welding, where the presence of O2 in the air would oxidize the fresh weld. Air is 78% N2, 21% O2, and 1% other gases. Plants require nitrogen to grow. The triple bond is too strong for most plants to get nitrogen straight from the air. The legume family of plants that includes beans and peanuts have special bacteria in their roots that can fix N2 from the air into nitrates such as NO3 that the plants can use as food or fertilizer. The nitrogen-fixing bacteria take N2 from the air and react it with water, H2O, to form ammonia, NH3. A further reaction of ammonia, NH3, with oxygen, O2, forms nitrates such as NO3 that plants then use as fertilizer. In solution with water, nitric acid, HNO3, dissolves into H+ and nitrate ions, NO3 negatives, that plants can use as food to grow. In nonpolar covalent bonds, the atoms share the valence electrons equally. On the other hand, polar covalent bonds are covalent bonds in which one component of the bond has a stronger pull on the shared electron than the other partner. When the shared electron is pulled closer to one atom, that atom becomes more strongly negatively charged. As the shared electron is pulled away from the opposite partner, the protons of the nucleus of that opposite partner expose their positive charge to the surroundings. The molecule has positively and negatively charged poles, or is said to be polar. And the resulting molecule is said to have a polar covalent bond. The water molecule is a good example of a polar covalent bond. The strong polarity of the water molecule is why water is active in hydrogen bonding. In a water molecule, the oxygen atom pulls the single valence electron of the hydrogen atom into itself. The positive charge of the hydrogen atoms, actually naked protons, will attract and grab any negative ions that float by the water molecule. This is hydrogen bonding. In fact, one water molecule will attach itself to another water molecule if the positively charged hydrogen comes in contact with the negatively charged oxygen part of the other water molecule. The fact that water molecules cling to each other results in the strong surface tension of water. The fact that water molecules cling to each other results in water having viscosity, a property of resistance to allowing objects to pass through the water. To pass through the water, the object must break the chain of hydrogen bonds. The viscosity of water causes it to resist dripping through small holes. Many oils, as well as honey, have higher viscosities than water because of the clinginess of their own molecules to each other. The clinginess of water, due to its polar molecules, causes it to wet the surfaces of other materials. When water is heated into steam or water vapor, the velocity and kinetic energy of the water molecules causes the hydrogen bonds to break and prevents the hydrogen bonds from reforming. When water is cooled to near freezing, the hydrogen bonds cause the water molecules to arrange into 6-molecule rings. As the water freezes, the rings join to each other with additional hydrogen bonds and ice crystals begin to grow. The fact that water molecules initially arranged into 6-sided rings causes the ice crystals to grow as hexagon shapes in solid ice, or as 6-sided snowflakes when the ice crystals condense straight out of water vapor. The fact that ice grows from 6-sided rings with a hollow center allows solid ice to be less dense than liquid water. The fact that solid ice is less dense than liquid water allows ice to float on the surface of ponds, lakes, and frozen seas. The fact that ice floats on water allows the sun to melt it in the spring and summer. If ice did not float, lakes and oceans would freeze from the bottom up. Lakes and oceans would remain solid all summer, and only the top few inches of ice would thaw during the summer. If ice did not float on water, life would be impossible on Earth. It is a gift from God that ice floats. Just because we can understand the science and chemistry of the hydrogen bonding that allows the ice to form into hollow rings that are less dense than liquid water does not diminish the wonder of this gift from God. This is a God whose works we can understand. This is not a God of the gaps in our knowledge, as some atheists say. Chemists have developed a quick way to determine whether two elements will form an ionic bond, a polar covalent bond, or a nonpolar covalent bond. They have measured each element's potential to donate electrons and called this measurement the element's electronegativity. Chemists use the electronegativity difference between two elements to suggest the type of bond they might form. The use of electronegativity to predict bond type is general, not absolute, as there will be many exceptions. The electronegativity scale is from 0 to 4, no units. A 0 means the element is highly likely to donate an electron. A 4 means the element is highly receptive to receiving electrons. A middle electronegativity number like 2 means the element is just as likely to be a donor as a receiver of electrons. Column 1 elements are likely donors of electrons. We can see from the figure that the column 1 elements are all electronegative 1 or less. This makes sense because the column 1 elements only need to lose one electron to get an octet of valence electrons. We can also notice from the electronegative charts that heavier atoms, the elements towards the bottom of the first column like cesium or francium, have the lowest electronegativities because not only are they column 1 elements, but they have 6 or 7 energy shells. Their outermost electrons are further from their nucleus, so the electric force of attraction between their positively charged nucleus and the negatively charged electrons in the outermost shells are the weakest. Column 17 elements, or the group 7A halogens, are likely receivers of electrons. We can see from the figure that the column 17 elements are all electronegative 2.2 to 4.0. So they are likely receivers of electrons. This makes sense because the column 17 elements only need to gain one electron to get an octet of valence electrons. We can also notice from the electronegative charts that the lightest elements towards the tops of column 17, like fluorine or chlorine, have the highest electronegativities because they have only 2 or 3 energy shells. Their outermost electrons are close to their nucleus, so the electric force of attraction to attract additional electrons is higher than heavier elements with 6 or 7 electron shells surrounding the nucleus. Chemists can use the electronegativity chart to predict the type of bond that will form. Subtract the larger electronegativity from the smaller electronegativity to get the chemical polarity of the bond. We are talking generally, not absolutely. Nonpolar covalent bonds generally have an electronegativity difference of 0 to 0.5. Polar covalent bonds generally have an electronegativity difference of 0.5 to 1.7. Ionic bonds generally have an electronegativity difference of 1.7 or greater. The electronegativity difference between elements in a bond is a general predictor, not an absolute definition. In general, electronegativity differences work fairly well. As examples, we can look at the bonds of NaCl, H2O, and O2. Chlorine has an electronegativity of 3.0. Sodium has an electronegativity of 0.9. 3 minus 0.9 equals 2.1. As 2.1 is greater than 1.7, the prediction is that NaCl will be an ionic bond, and it is. Oxygen has an electronegativity of 3.5. Hydrogen has an electronegativity of 2.1. 3.5 minus 2.1 equals 1.4. As 1.4 is less than 1.7 but greater than 0.5, the prediction is that H2O will be a polar covalent bond. In fact, as 1.4 is so much greater than 0.5, we can predict that H2O will be strongly polar, and it is. As the electronegativity difference between two oxygen atoms is 0, the bond is nonpolar, and the valence electrons are equally shared between the two oxygen atoms in the bond. From what we have learned about chemical bonds, we can state in general. Metals bond with metals by metallic bonding. Metals bond with nonmetals by ionic bonding. Nonmetals bond with nonmetals by covalent bonding. And this concludes my video on chemical bonding. In my next video, I will discuss balancing chemical equations. Thank you for watching. If you enjoyed my video and would like to help me make similar content, please hit like and subscribe.